In this video, we're going to introduce the concept of a system of equations. So we've looked at a variety of equations so far. Most of the equations we've seen have actually represented a function. So remember, a function is going to be a relationship between an input and output where every input matches to exactly one output. If we use the variables x and y rather than using actual function notation, then we have an equation that has two variables. So what we're going to look at in this section and in some of the following sections is what we call a system of equations. So imagine putting more than one equation that has those two variables in it into the same problem together. So systems of equations are often used to solve resource allocation problems, specifically situations where we have multiple limited items, but they have to be used simultaneously to reach a goal. So essentially think of problems where somehow the variables are related to one another, but we want to know specifically what values would these variables have to take on in order to meet the certain requirements we have for the problem. So why do we have problems like this? Why do we need more than one equation to solve for these different variables? Well, the general rule with solving an equation is if you want to solve for one variable, you have to have one equation. As long as your one equation has exactly one variable, then you can isolate that variable and you can solve for it. Imagine instead that you have an equation that has two variables. What would you do to solve an equation like that? Well, you could isolate one of the variables, but that ultimately leaves the other variable in the problem. It doesn't uniquely solve for a specific constant value for that particular variable. It just gives you an expression for that variable in terms of the other. So for instance, if you isolated the variable y, you now have an expression involving x. If you isolate the variable x, you have an expression involving the variable y. You didn't actually solve for the variable in the sense of finding a value for it. So if you want to find a specific value for those two different variables, you're required to have at least two equations. So whenever you want to solve for more than one variable, actual concrete values for those variables, you're going to need multiple equations. So what we create when we have all those equations together is what we call a system of equations. So the system of equations is going to represent the relationship among the variables, but it represents that relationship where we have more than one equation giving us information about how the variables are related. So let's look at a very simple applied situation where we might use a system of equations. We're going to write the system, and then what we want to talk about in this section is after we've written it, how do we actually solve for the variables in our system of equations? And we're actually going to look at three different techniques for solving. So here's our basic example. If two adult tickets and one child ticket for something cost $32, so that particular purchase cost $32, and if one adult ticket and three child tickets cost $36, then what is the price of each kind of ticket? So if you see a problem like this, your immediate thought might be guess and check. So just pick some values, plug them in, see if they work. Technically, yes, you can do something like that. The problem though is what happens if the prices for these tickets are not whole dollar amounts? What if they involve cents? What if something is $1.25, something like that? Essentially the big takeaway is you would potentially have to guess and check a lot of different values. And ultimately that's not the most efficient technique to use to determine what values would actually make these particular relationships true. So we need something a little bit more efficient, a little bit more effective than just guessing the price of an adult ticket, guessing the price of a child ticket, and seeing if the values actually work. Now, if we only had the one relationship, if we were told that two adult tickets and one child ticket cost $32, and we weren't given anything about the other purchase, that would not actually be enough information to uniquely solve for those particular values for these particular items. So we can pick different combinations of adult prices, a different combination with a child price. There are different combinations of values that would add up to give us $32. So just based on having that one piece of information, we can't definitively say an adult ticket costs this much, a child ticket costs this much. we have to have the two different pieces of information here in order to uniquely determine what the price is for each of these individual items. So what we want to do, rather than just guessing values, checking and seeing if they work, if they add up to $32, if they add up to $36, what we want to do is we want to represent these two pieces of information in equation form. Ultimately, what we're focused on is what are the variables, how do these variables fit into an equation, and then of course, how would we actually solve for the values of those variables based on the equations that we have. So anytime we have a problem like this, we're attempting to find a value, more than one value, first thing we need to do is determine what are we actually trying to solve for? What are we actually looking for? Well, in this case, the question is, what is the price of each kind of ticket? So we have two kinds of tickets. We have an adult ticket, we have a child ticket, and the question is, what's the price of each of them? So those are going to be our unknowns. Those are going to be our variables. Notice we're looking for two different values, so we're going to need two different variables. Now the variables you assign, ultimately that can be arbitrary, but because we're going to focus on different things that can be graphed, ideally we want to pick X and Y, and then eventually when we add on a third variable, we're going to add on the variable Z, which relates to a third dimension. So the first variable we're going to assign as X. X is going to represent the price of an adult ticket. So whatever value we get for the price of an adult ticket, that's going to be the value for the variable X. And then the other value we're solving for is the price of a child's ticket, and we're going to let that be the variable Y. So these are the two unknowns we want to solve for. And now we have to represent our two pieces of information using these variables. So each piece of information we're given is going to give us one equation. So the first piece of information we've been given is that two adult tickets and one child ticket cost $32. Well, how would we represent that with an equation? We have to think about what our variables represent and how they relate to the number of items being purchased. So in terms of the variable X represents the price of an adult ticket. Well, we bought two adult tickets. So if you think about that component as contributing towards the total of $32, if you were to multiply 2 by the price of each of those two tickets, then that would give you the portion of the total that contributed towards the entire total of $32. So the number of tickets multiplied by the price of the ticket is going to give you that particular portion of the total of $32. Now, same thing with the one child ticket. We bought one child ticket. If we multiply the number of tickets we bought by the price of that particular ticket, then that also is going to give us that portion of the total that was contributed from that ticket. So 2 times the price of an adult ticket, 1 times the price of a child's ticket. Both of these are part of the same purchase, so we'd add those two values together, and the total from that addition should give us 32. So putting that all into equation form, that's going to be 2 times X plus Y, so 1 times Y, we just write that as Y, and that is going to be equal to $32. So the first piece of information we have, this would be the equation representing that piece of information. Now we also have a second piece of information representing a second purchase. So 1 adult ticket and 3 child tickets cost $36. So 1 adult ticket multiplied by the price of that ticket, that gives us that portion of the total, 36. And then 3 child tickets multiplied by the price of a child ticket gives us that portion of the total. Again, we add those two together and they should add up to the total of 36. So 1 times X, again, we don't write the 1, but 1 times X plus 3 times Y adds up to a total of $36. This is a system of equations. So it's a pair of equations representing this situation and ultimately representing the relationship among these two variables, X and Y. So with only one of these equations by itself, we can't uniquely solve for x and y. We could have different combinations of x and y values that make the equation true, but we can't officially say this has to be the value for x, this has to be the value for y, and we can determine that uniquely. We have to have the two equations and we have to solve them in tandem in order to determine what the values for x and y are going to have to be to make both of these equations true. So let's define a system in general. So a general system of equations with two variables, two equations, is going to be of this form. So x and y, we're still going to think of those as our variables. A, B, C, D, H, K, those are all arbitrary, but we're going to think of those as constants. So A, B, C, and D are going to be the coefficients for our variables in each of our two equations. And then H and K are going to be the constants that our equations are equal to. Now keep in mind, this is what we can think of as more of a standard form for a system of equations, but not every system of equations will be given in this form. We can have things rearranged, we can have things on different sides of the equations, we can move terms around, and ultimately, as long as we're considering both of these equations together at the same time, it still represents a system of equations. Ultimately, for what we're going to want to do, this is going to be the form that's going to be most useful. So having both of our variable terms on the same side of the equation and then having a constant on the other side of the equation. So a solution to this system, something that actually solves the system in terms of what are we actually solving for, what kind of answer are we looking for, the solution to this kind of system is going to be an ordered pair, so something of the form x comma y. Keep in mind, x and y are the variables. Those are the things we're solving for. So what we're looking for are values for x and y. Well, we can express those as an ordered pair because they go together. We have a value for x, we have a value for y, we pair them up. But specifically, it has to be an ordered pair that satisfies both equations. So we have to find the unique value of x and the unique value of y that's going to make the first equation true while also making the second equation true as well. What you'll find, particularly if you look at a problem like this, and for instance, you try the guess and check method, you may be able to find an x and y pair that make the first equation true, but the odds of immediately picking a pair that also make the second equation true are pretty slim. So what we're looking for is what pair of values makes both equations true at the same time. Whatever pair of values does that, that is going to be the solution to our system. It's the x and y that are going to work in both equations at the same time. So ultimately the question then becomes, how do we find that x value and how do we find that y value? Well, if we're looking for an ordered pair, immediately ordered pair, think graphing. Ordered pairs can be graphed, equations can be graphed. Well, if we're looking for an ordered pair that makes the first equation true and makes the second equation true, how would that correspond to a situation when we're graphing? Well, we can think of it in that situation as any ordered pair that they have in common. How would we know they have it in common? Well, they have that particular ordered pair in common if that particular point representing that ordered pair is going to be on both of the equations' graphs. Well, if we're talking about linear equations like this, we're talking about straight lines. How do we know these are linear? Well, both of our variables have an exponent of 1, so that means our first equation will graph as a line, and then the second equation will also graph as a line. If we're looking for an ordered pair that these two equations have in common, something that satisfies both of them, then what we're ultimately looking for is where these two lines are going to cross. An ordered pair or a point they have in common can be recognized if we can see a location where they cross, where they have something in common there on the coordinate plane. So if we can determine where these two lines would cross, that particular location and the associated x and y values represent the solution to our system. So what we're going to look at first is how we would solve our system by graphing. So ultimately, we just want to graph these and we want to identify any location or locations where these particular equations, where their graphs are going to intersect. So there are a variety of different ways to graph something linear. More than likely, when you took your first algebra class, you learned a lot of different ways to graph something that's linear. One way to graph is using intercepts, and we've looked at that a little bit before when we were looking at functions, talking about just generic graphing techniques. You can always find intercepts, and remember the general rule for an intercept is if you're solving for a particular intercept, you're going to let the other variable's value be 0. If one particular variable's value is 0, then graphically speaking, that means we're crossing somewhere on an axis. So if we want an x-intercept, we're going to allow the y to be 0. And if we want a y-intercept, we're going to allow x to be 0. Now we have two equations, so we're going to have to find the intercepts for each of these equations and graph each of them individually. So let's start with the first one. 2x plus y is equal to 32, or specifically $32. So for our x-intercept, we're substituting a 0 in place of y. And so essentially that's going to make that particular term go away. So we have 2x is equal to 32. If we solve for x, divide by 2, that's going to give us x is equal to 16. So the x-intercept for this particular equation is going to be 16. Now the y-intercept as well. Now we're going to substitute a 0 in place of x, which again is going to eliminate one term, and it's going to leave us with y is equal to 32. So that is going to be our y-intercept. 2 points uniquely define a line. So this is going to give us 2 points that we can graph that will uniquely define this particular line. Now before we put it on the graph, let's look for the other intercepts as well, and then we'll do it all at one time. So our other equation was x plus 3y is equal to 36. So for our x-intercept, we let y be 0, which eliminates this term. So we know that x would have to be 36 in order for that relationship to be true. Now for our y-intercept, we're going to allow x to be 0, which eliminates that first term. So it leaves us with 3y is equal to 36. We divide by 3 on both sides, and we get y is equal to 12. Now you'll notice that these are fairly large numbers, at least from the standpoint of graphing. Your standard coordinate plane you typically have is about a 20 by 20, so 10 units either direction along the x-axis, 10 units either direction along the y-axis. Well, the smallest value we want to graph here is 12. That's the smallest value. And then the highest value we want to graph is 36. So the basic coordinate plane we typically have is not going to cut it. So one option here is to actually graph using a different scale. So if we have just a generic coordinate plane and we don't actually have any units written, if we can change the scale to something that's a little bit more manageable, then that may allow us to graph this a little bit more easily. So ultimately, we want to pick a scale that's going to allow us to graph all of these numbers without too much trouble. How do we know what kind of scale to pick? Well, we want to pick a scale, ideally, if possible, where each of these values would fit on a whole unit on our scale. What does that really mean? Well, what we're looking for is a particular scale where we count by a number that would divide into all 4 of these particular values, the actual ones we want to graph. If we can find a number that divides into all 4 of those and use that number to represent our scale, then we know that all of these numbers are going to fall on the grid and they're not going to fall in the middle between the actual tick marks. Well, they're all even numbers, so 2 would definitely divide into all of them. But if we count by 2s, we're still going to need, let's see, that would be 13 2s in order to get up to 36. So we'd still need to be able to count out to 13, which again, we may not really have the option to do. Now, another number that actually divides into all 4 of these is going to be 4. Let's verify that. So 16 is divisible by 4, that divides in evenly. 32 is divisible by 4. Let's see, 36 is divisible by 4, and then also 12 is divisible by 4. So as long as we can find a number that divides into all of these values, then that scale is going to work and it's going to give us something fairly straightforward to graph by. So rather than counting by units of 1, we're going to count by units of 4 along the x-axis and along the y-axis. Now you'll notice that the coordinate plane I provided is kind of unique. It's actually only one quadrant. This is what we think of as the origin, rather than thinking of the origin as being in the center of the grid. So ultimately, this represents just the first quadrant in the coordinate plane. Now, why is that? Why can we just use the first quadrant? Well, when we're talking about real-world problems, talking about allocating resources, you have to think about what kinds of numbers would actually solve a problem like that. What would a negative number mean in the context of a problem like this? Well, for instance, our particular problem, we're talking about prices for tickets. So what would a negative answer for X or for Y actually mean? Well, it would mean we have a negative price for a ticket. Ultimately, something like a negative price for a ticket doesn't actually make sense. So if this problem is in fact a problem that we can solve, then we should not get any negative answers, because negative answers won't really make sense in the context of this problem. We know that X is going to have to be a non-negative number, and Y should also be a non-negative number in order to make sense in the context of this kind of problem. So if we're exclusively looking at non-negative X and Y values, ultimately all we need is the first quadrant of the coordinate plane. We're actually going to find that in most problems we do, particularly applied problems, all we really need from a graphing standpoint is going to be that first quadrant, because we run into a lot of situations where negative numbers just don't really make any sense in the context of the types of problems that we're solving. So we're just looking at the first quadrant, just looking at positive numbers, and we decided that in order to graph all of these values a little bit more easily, we're going to count using a scale of 4. Now the highest number we have to get out to is 36, so that's as far as we need to go. We can keep labeling from there if we want, but that's going to be the furthest out we have to go. So labeling by 4s along the x-axis, and then in order to be consistent, also labeling by 4s along the y-axis. So once we've done that, we want to graph our intercepts. Now keep in mind which ones go together. So 16 and 32. So 16 is our x-intercept, and then 32 is going to be our y-intercept. Once you have those 2 points, take a ruler, connect your dots. Now try to be as accurate as possible when you're graphing. It's going to be a little bit more important than it was before, simply because we're graphing more than one thing, and if we're looking for things that these two graphs have in common, the more accurately we graph, the more accurately we can interpret what we're seeing on that graph. So that's going to be our first line, and again, notice it stops. Technically a line continues in both directions, but we're only looking at the portion of this line that's confined to the first quadrant. Now for our next line, we have an x-intercept at 36, and we have a y-intercept at 12. So we also want to connect those dots, again defining that particular line. So again, we define our solution as whatever ordered pair or ordered pairs satisfy both equations. In other words, whichever ones they have in common, which are represented on the graph by any locations our lines would cross. So if we can find a location where our lines cross, that represents an ordered pair that our two equations have in common. It's that point that the two lines have in common. Well, in this case, there's a very clear point that they have in common. And the more accurately you graph here, the easier it's going to be to identify what the actual coordinates are for that point. Now, as we identify the coordinates, keep in mind, we didn't count by 1s, we counted by 4s. So in interpreting what the coordinates are for this point, we also have to consider the scale that we used. So in order to get to this point, the point we're looking for, we would have to travel 3 units horizontally. We're counting by 4s, so 3 units counting by 4 would be 12. And then 2 units vertically, again counting by 4. So 2 units vertically, counting by 4, would give us 8. So the one ordered pair that these two lines have in common is going to be the ordered pair 12 8. So if we have two diagonal lines that cross uniquely at this one point, this will be the only point where they cross. If you imagine what the lines look like continuing out, based on the shape of a line, there's no location where they could cross again. So this will be the one unique location where these lines cross. So we now know the unique x and the unique y value that represents that ordered pair that solves our system. So x equals 12, y equals 8, that's our solution. Now let's put that back in the context of the problem though. What was the problem asking for? It was asking for the price of each kind of ticket. So keyword here is price. So what we're solving for, those two numbers represent prices. So x represents a dollar amount, and then y represents a dollar amount as well. So x is $12, and then y is going to be $8. So supposedly, these are the two unique x and y values that satisfy, that make true both of these equations. Now we can actually verify that these values work just like we do any other time we solve an equation. If you plug these numbers back into the equations, then they should give you true statements. But here, you need to be able to plug it back into both equations and verify that both of them are going to be true. So let's verify that. So the first equation, we want to make sure that x equals 12 and y equals 8 make this equation true. So 2 times our x value, which is going to be 2 times 12, plus our y value, which is going to be 8, do in fact give us 32. So this pair, 12 and 8, make the first equation true. Now what about the second equation? So now we're taking x, which is 12, and we're adding on 3 times y, which is going to be 8. And again, that's going to add up to give us 36, which is what we want. So that confirms that these are in fact the unique x and y values that are going to make this equation true. Now let's look at a few more examples. We'll take it out of context for a moment, but I want to show you some of the other possibilities. There are a variety of different ways that lines can look when you graph them, and based on the context of a system of equations, this can mean a couple different things for the kind of situation we're looking at from the standpoint of solving our system. So here's our next system. We have x minus 2y is equal to 2, and x plus y is equal to 5. Now again, each of these individual equations, if we took away one and just kept the other, there's no way to uniquely determine an x and y value that make it true. So it's easiest to see that from the second equation. So x plus y is equal to 5. Imagine that first equation was not there. Well, what could we say about the second equation? Well, x could be 1, which means y would have to be 4. But is that the only x and y pair that solve that equation? Well, of course it's not. So we could have 1 and 4, we could have 2 and 3, we could have 0 and 5. We have a bunch of different possibilities. So one equation with two variables actually has a bunch of different ordered pairs that solve it. As it turns out, if we were to graph that equation, then any ordered pair represented on that individual line would solve that individual equation. If we want to find a unique x value and a unique y value, we have to have the two equations to allow us to solve for the two variables. So two variables, we need at minimum 2 equations. 3 variables, we need at minimum 3 equations, and then so on and so forth. So let's solve this particular one again by graphing. So let's start with our first equation. We want to graph that. Again, let's just focus on using our intercepts. So for our x-intercept, we want to solve for x by allowing y to be 0. So we're going to substitute a 0 in place of y, which means that second term is eliminated. So we have x is equal to 2 as our x-intercept. Now for our y-intercept, we're going to let x be 0, sub in a 0 there. Now be very careful right here. Notice what happens when you sub in a 0 and that first term disappears. What you're left with is not 2y, you're left with a negative 2y. That negative is going to be important here because when you divide out that negative 2 on both sides, it's going to give you y is equal to negative 1. If you drop off both the 0 and the negative, and then solve for y, that would give you a positive 1 instead. That will drastically change the problem. So be very careful with your signs, particularly in a situation like this. So x-intercept at 2, y-intercept at -1. So x-intercept at 2, y-intercept at -1, and that's going to be the line we get when we graph that particular one. Okay, now x plus y is equal to 5. Again, substitute a 0 for y, which gives us x is equal to 5. That's going to be our x-intercept. And then substitute a 0 for x, which gives us y is equal to 5 as our y-intercept. So an x-intercept at 5, and then a y-intercept at 5 as well. Again, try to graph these as accurately as possible. Great attention to detail, because ultimately we're looking for where these two graphs cross. The more accurate your original graphs are, the more accurately you can identify the location where they cross. So in this case, they're going to cross at the ordered pair 4, 1. So that's going to be the solution to this system, the ordered pair 4, 1. Again, we can verify that those two values are correct by substituting them into our two equations and making sure those equations are true. So you might consider doing that. Now, there are actually two other situations we can run into based on having a system of equations. So this situation is basically the same as what we saw with that applied problem. Ultimately, we're focused on the fact that there is truly a unique x value and a unique y value that solve this system. Unfortunately, that's not always going to be the case. There are actually two different situations that we can run into that represent possible outcomes for a system of equations. So let's look at another one. So x plus 2y is equal to -4, and 2x plus 4y is equal to 8. So again, we want to graph these two lines using their intercepts, and then we're looking for any locations where these lines are going to cross. So for our first line, let y be 0. That's going to eliminate our second term, which gives us an x-intercept at -4. And then also let x be 0. That eliminates our first term, leaving us with 2y is equal to -4. We divide by that 2, and that's going to give us y is -2. So this particular line has an x-intercept at -4 and a y-intercept at -2. So that's going to be that line. Okay, next one. 2x plus 4y is equal to 8. Substitute a 0 in place of y, which leaves us with 2x is equal to 8. Divide by 2, so x is going to be 4. And then also substitute a 0 in place of x, which eliminates our first term. Divide both sides by 4, and we're going to get y is equal to 2. So intercepts at x equals 4, and then y equals 2. Now notice what happens when these two lines are graphed. We definitely cannot see any locations where they cross on the coordinate plane so far. And as it turns out, if you were to blow up the coordinate plane, look further, look out in the distance, see what the lines look like as we go out towards positive and negative infinity, it turns out you're still not going to find any locations where they graph. These two lines have what we call the same slope. The way they are oriented in terms of how steep the line is and which direction the line is oriented as we go left to right, these two lines have the same slope. But because one is further up on the coordinate plane than the other, there's not actually going to be any location where they cross. There's a name for these two types of lines. These lines are parallel. Well, ultimately, if our solution is represented by some location where our lines touch or cross, these lines don't ever touch and they don't ever cross. So that means this particular system does not actually have a solution. Whenever our two equations have the same slope and we graph the lines and they are parallel, that means that our system has no solution. We cannot actually uniquely find an x and a y value that satisfy both of these equations at the same time. Now, I want to make a distinction here. That doesn't mean you couldn't find an x and y value to make the individual equations true. You can actually find infinitely many x and y values that make the individual ones true. So for instance, the first equation was represented by that bottom graph. Any xy pair anywhere on that line would satisfy that equation. But we can't find an xy pair on that line that also makes the first equation true at the same time. So any ordered pair that satisfies the first equation doesn't satisfy the second. Any ordered pair that satisfies the second equation also doesn't satisfy the first at the same time. So they don't have any ordered pairs in common. Ultimately, we're looking for things they have in common. Here, they don't have any ordered pairs in common, so there is no solution. Now, there's one other possibility that may not be as obvious, but it's a very unique, very rare situation. So let's graph these two lines. So 2x plus 4y is equal to 8. Hey, we already graphed that one. So we already know that that particular one has intercepts at x equals 4 and y equals 2. So there we go. Okay, now what about the next one? So x plus 2y is equal to 4. So for our x-intercept, we're going to let y be 0. That eliminates that second term. So we get x is equal to 4. And then for our y-intercept, we're going to let x be 0. So we have 2y is equal to 4, divide by 2, and we get y is equal to 2. Well, notice when I graph these two values, x equals 4 and y equals 2, they actually coincide with the intercepts we had for the first equation. Well, if 2 points uniquely define a line, then these two intercepts uniquely define the graph of this line. But when we graph this line, because we graph with the same intercepts, we actually get a graph that just lays on top of it, coincides with the graph we already have. These two lines coincide. They are collinear. They lay on top of one another because, believe it or not, they're actually the same equation. So you look at these two equations, and yes, they have different numbers. We have 2, 4, and 8, and then we have 1. It's not written, but there's a 1, 1, 2, and 4. But I want you to think of what would happen if you took that first equation and you reduced it. What do I mean by that? Well, look at all the coefficients. We have a 2, we have a 4, and then we also have an 8 on the other side of the equation. What do all of those numbers have in common in terms of a number that could divide into them? Well, they all have a 2 in common. So we could actually take that first equation and we could reduce it by dividing a 2 into all 3 of those terms. Well, what would happen if we did that? If we divided a 2 into the first term, the 2 goes away and we're just left with x. If we divide a 2 into the second term, 4 divided by 2 is going to give us 2. And then if we divided 2 into the last term, the constant by itself, 8 divided by 2 is going to give us 4. So these two equations only differ by a constant multiple. If they only differ by a constant multiple, then what that ultimately means is that all of the same x and y values that make the first equation true will also make the second equation true. Because ultimately, we could take that first equation, divide out that 2, and we would still have the same x, the same y. And ultimately, the relationship we would then have modeled would be the same relationship as what we have for that second equation. So these two equations may not initially look the same, but in terms of their structure, in terms of the relationship they're representing, they actually represent the same relationship. So the two graphs, one lays on top of the other. If our solution to our system is defined as any points that would make both equations true at the same time, well, one graph coincides with the other. So what that actually means is they have every single point in common. Every point on this line is also a point on this line because they're actually the same equation and their graphs are actually the same line. So in this case, we have infinitely many solutions. Now, I want to make a very important distinction here. You may see that term infinitely many, and you may immediately think all real numbers, if you've heard the term all real numbers before. That is not what's happening here. All real numbers literally means every possible number. So it's true and it's not true. What we're ultimately looking for here are paired x and y values that would make this equation true. Well, we can have any x value we want because our lines stretch out horizontally forever and ever and ever. But it's not literally every x value and every y value in the sense that we can just pair up whatever numbers we want. There are infinitely many solutions, but the solutions all have to be ordered pairs that fall on this line. So one of the solutions would be 4, 0. One solution would be 0, 2. And then any other solution, any other ordered pair that falls on this line would also be a solution. So for instance, it looks like 2, 1 would be a solution. It looks like negative 2, 3 would be a solution. The infinitely many solutions, it's going to be all of those ordered pairs that we can find. So we cannot say that the solution is all real numbers. All that we can say is that we have infinitely many solutions, and they're represented by all the ordered pairs that would fall on each of those coinciding lines. So we do have to be very careful about what we say when we're saying there's more than one solution, there's infinitely many. It's infinitely many, but it's infinitely many based on these ordered pairs that we can find on these two graphs based on their equations. So these represent the 3 unique situations we're going to find when we solve a system of equations. Every system we solve is going to fall under one of these 3 cases. And based on each of these 3 cases, based on what we see in terms of how many solutions we find, what kind of solutions we find, we can categorize our system in a specific way. So if there is exactly one solution, which would be this case, there's exactly one ordered pair that solves our system, then we would say that the system is consistent, which just means it does have a solution. Consistent means we can find a solution, but it's also independent. The independence here means that the 2 equations are independent of one another. In other words, we get unique pieces of information from each of those individual equations. Each of them does contribute something concrete to the solution to the system. So one equation is independent of the other. Now, if there is no solution, like in this second case, then we would say that the system is inconsistent. Inconsistent just means we cannot actually solve it, there is no solution. The term independence doesn't actually relate here. Independence is used to categorize systems where we could find a solution. If we can't find a solution, then period, we can't find a solution. Now the last case was where we had infinitely many solutions. So we can solve the system, it is consistent, but in this case, the equations are dependent. In other words, the actual solution individually that we find is dependent upon the relationship that's modeled by this particular pair of equations, which again, we determined they're actually the same equation. So in this case, finding a solution is dependent on having a little bit more information. If we were to pick an X value, we can find an associated Y value, but we can't find a unique, independent, single ordered pair that solves this system. Now, sometimes graphing will not be a great option for solving a system. It does technically always work, but graphing in terms of its accuracy is limited on how detailed we can be. So what do I mean by that? Well, say for instance, we graphed these 2 lines, but they didn't cross on a grid line, a pair of grid lines. What if they crossed somewhere between grid lines? Maybe they're on one grid line, but they're between another pair of grid lines. Maybe the vertical grid lines, they're between 2 grid lines. Well, how do we know exactly where our lines are crossing if we're just trying to identify a point in space from a line? How do we know if they're crossing halfway between the grid lines or maybe a third of the way between them? Well, ultimately, the answer is if we only have a graph, we don't actually know. We're limited as to how accurately we can graph, and the accuracy of our solutions is limited based on how accurate our graphing tools are. So graphing may not always be the best option for solving a system, particularly in cases where we're limited and we only have a small coordinate plane, something like this. So it's great in terms of a visual, but in terms of efficiently solving a system and saying this is a technique that always works, we're not limited based on our tools, ultimately we're going to focus on algebraic methods for solving our systems. Regardless of how complicated the equations look and how nasty the graphs would look in terms of maybe where they cross, the algebraic solution techniques are always going to work every single time. So we're going to look at 2 different algebraic techniques that we can use, and we're going to go back and we're going to revisit those ones we just graphed. Ultimately, every system, regardless of how you solve it, should have the same solution. So if we're saying that more than one solving technique works, then ultimately we should get the same solution every single time we solve the system, regardless of the method we use to solve it. So the first algebraic technique we use is called substitution. So ultimately, we're going to substitute something. Now, what are we going to substitute? We'll talk about that. So this particular method is going to be a good option to use when you can easily isolate a variable. So when you can look at least one of your equations, just got to have one where this works, and you can isolate a variable easily. Now, how do you know when it would be easy to isolate a variable? If you can look at your equations and you can find a variable, at least one of them, that has a coefficient of 1, in other words, you don't see a coefficient written, then that means that variable would be easy to isolate. Ultimately, what we're looking to avoid is any algebra that would create fractions. So if isolating a variable would require you to divide out a number. So say, for instance, something like this right here, we have a 2y, or specifically a negative 2y. If we wanted to isolate that y, ultimately, we would have to divide out the negative 2 that's multiplied by it. By dividing out that negative 2, it is entirely possible that we would create fractions where there weren't any fractions before in our original equations. So we want to avoid trying to isolate anything that would require us to divide out a number and then potentially create fractions. If we can find a variable where that's not going to be required, all we need is one equation with one variable that looks like that has a coefficient of 1, and that will be the variable that we want to isolate. So what we're going to do is we're going to pick that variable. We're going to use whatever algebra we need to isolate that variable. So get the x by itself, get the y by itself. It's just going to depend on what we choose. What we're then going to do is we're going to substitute the expression for that variable into the other equation. So what we'll find, say we solve for x, we'll have x is equal to some expression involving y. Ultimately, what that means is that anywhere in the system, wherever you see an x, you could also substitute this particular expression involving y because they're the same. So if they're the same, any place you see one, you could put the other. The result is then going to be a new equation that only has one variable in it, and once we have an equation with one variable, we can solve. So all of that sounds really vague. Let's actually put it with some numbers. So we're going to take the same 3 that we looked at before, and we're going to solve each of these 3 using substitution instead of using graphing. So if you remember the first one, the solution was the ordered pair 4, 1. The second one was no solution. And then the third one, we had infinitely many solutions. How would you identify these last 2 special cases algebraically? Well, we'll talk about that as well. So for our first system, I like to label the equations with a number. So in parentheses, I'm going to put a 1 for equation 1 and a 2 for equation 2. Ultimately, I do this because we have to make sure that we use both equations as we're working. If we exclusively use one equation and don't use the other, then ultimately we can't guarantee that we've actually definitively solved the system. So I'm going to use equation 1, equation 2. I'm going to pick one of these equations where it would be easy to isolate a variable. Now again, what are we looking for? We're looking for at least one variable that has a coefficient of 1. Now, as it turns out, we have 3 different variables, 3 different terms where there's a coefficient of 1. So in the first equation, our x has a coefficient of 1. And in the second equation, both x and y have coefficients of 1. Any 3 of those would be acceptable variables to isolate. It does not matter which one you choose. You can choose either one. Just because this is the first one I see, I'm going to pick the first one. I'm going to pick the first equation, and I'm going to isolate x. So I'm going to label that I'm using equation 1 because, again, I have to make sure that I use both. I'm using equation 1 now, which means that I'm then going to have to use equation 2 later. So what I want to do with equation 1 is I want to isolate that particular variable that I've chosen. In this case, I'm isolating x. So the goal is to move everything else to the other side of the equation so that the x is by itself. So we have x minus 2y. So ultimately, we want to take that negative 2y. We want to move it to the other side of the equation. Now, it is subtracted here, which means that if we want to move it over, we have to take that term and we have to add it, and that's going to move it to the other side of the equation. So if we add a 2y on both sides of the equation, well, this 2y is eliminated, and that gives us a 2y on the other side of the equation. So we're left with a new version of the equation, just one where x is by itself. So we have x is equal to 2 plus 2y, or you could write 2y plus 2, your choice. Now what we have is an expression for x involving the variable y. What we now have is an expression that represents x in terms of the other variable. So what this tells us is that wherever there is an x in this problem, we could put a 2 plus 2y instead, because ultimately they are equal. They mean the same thing. If we know x is equal to 1, then we know 2 plus 2y also has to be equal to 1, because these two things are in balance and they're set equal. So what I'm going to do now is I'm going to use this piece of information and I'm going to substitute into the other equation. So I've used equation 1. Now I have to use the other equation, the one I haven't used, equation 2, which is x plus y is equal to 5. So using this piece of information, which tells me x is equal to 2 plus 2y, I'm going to substitute for the x with this equivalent expression involving x, which is 2 plus 2y. So x, I'm now going to replace with 2 plus 2y. I'm plugging it in place of that variable. Notice I put parentheses around it. Whenever we substitute, remember we talked about this with functions. Whenever you substitute something in place of another thing, a value for a variable, get in the habit of putting parentheses around it. Now, what does that accomplish for us? It takes an equation with two variables, and it now gives us an equation that only has one variable. The new equation we get after we do that substitution is now an equation that only has the variable y. Well, if it's an equation that only has one variable, that means we can now isolate that variable, and it won't be a new expression involving another variable. It'll be an actual concrete fixed value. So our goal now is to take this new equation and to isolate y, solve for y. Well, we need to combine our like terms first. So we have 2y's plus another y, 3y's in total. So on the left-hand side, we have 2 plus 3y, and then on the right-hand side, that's equal to 5. Now again, the goal is to get y by itself. So I need to move the 2 over first. So I'm going to subtract 2 from both sides. The 2 is positive, so subtract it. That gives us 3y is equal to 3. 3 is multiplied by y, so be careful here. We're going to divide it. So 3y divided by 3, and then divide by 3 on the other side as well, is going to give us y is equal to 1. Now we're not entirely done. That's only half of our solution. But remember, we need an ordered pair. We need an x value and a y value. Here's where I'm going to go back to that expression I found for x. I know that anywhere in this equation, anywhere in this system rather, x and 2 plus 2y are the same thing. Well, we know y specifically has a value of 1. So I can use this expression I have for x, and I can substitute in this value I just found for y. So I'm going to do that over here. So we know x is equal to 2 plus 2y. I'm going to substitute in the value for y that I just found. So we have 2 plus 2 times 1. Well, 2 times 1 is going to be 2. So 2 plus 2 is going to give me 4. That's going to be my value for x. Now this particular step where we solve for x, you actually have a variety of options here. You could go back to either of the original equations and plug in your y value and solve for x, or you use the version where you already isolated your x. It's ultimately your choice. You can do it either way. This is typically an easy spot to substitute just because we already have our variable isolated. So our ordered pair is going to have an x value of 4, and it's going to have a y value of 1. So our solution is going to be 4, 1, which was also the same ordered pair that we got from graphing. Okay, let's look at another one. Remember, the other two were the special cases. How do I identify those special cases? Well, unless you know immediately what to look for with the equations, you just proceed like normal. You'll apply the same technique we applied here. What you're looking for are some special indicators a little bit further down the road in terms of the algebra. So again, I'm going to label equation 1. equation 2, I'm looking for a variable in a particular equation that would be easy to isolate. So ideally an equation and a variable with a coefficient of 1. In this case, the only variable with a coefficient of 1 is going to be x in equation 1. So I'm going to use equation 1 here, and I specifically want to isolate the variable x because that's the only variable I can isolate without having to do any division to get rid of a coefficient. So we have x plus 2y is equal to -4. I need to move my positive 2y, so I'm going to subtract it on both sides, and that's going to move it over and isolate the x. So we have x is equal to -4 minus 2y. So again, what we now have is an expression for x involving the variable y. So wherever we have an x in this problem, we could put a -4 minus 2y instead because we know that they represent the same thing. We know that they're equal. So I've used equation 1. Now I have to use equation 2. So in equation 2, we're going to substitute for the x. So wherever I have an x, I'm going to put my -4 minus 2y. And again, make sure you put parentheses around it. Here, it wasn't a huge deal, but here it very much matters. The reason it matters is because 2 is multiplied by x, which means that 2 has to be multiplied by whatever we substitute for x. What we have to do here is distribute. We're going to have to distribute that 2. We can distribute here without any problems. There's no exponent. It's literally just 2 multiplied by both of these terms in parentheses. So I'm going to take the 2 and multiply by each of these individual terms, which gives me a -8. So 2 times -4 is -8. And then 2 times -2 is -4y. Now we still have a plus 4y, and then that's equal to 8. Now what happened here on the left-hand side? We distributed and ended up with a -4y, but we already had a positive 4y from the actual equation. These are equal and opposite terms. So they are like terms, but when they combine together, because we have a -4 and a positive 4, these two terms reduce down to 0. The question is, what are we left with? Well, unfortunately, we don't have any variables left. As soon as you eliminate the variables entirely, immediately that means you're in one of the two special cases. If you don't eliminate a variable, for instance, in this situation, we simplified, but we still had a variable. That means you're going to be able to solve for a unique value for x and a unique value for y. In this case, there wasn't a mistake. We didn't make a mistake, but the algebra was such that all variables were eliminated. So we substituted, which eliminated x, but the resulting algebra then just eliminated the y as well. The question then is, what are we left with? What we're left with is going to tell us which special case we fall under. So on the left-hand side, notice that we have a -8. That negative is very important here because on the right-hand side, we have a +8. So once the variable terms are eliminated, we're left with the equation -8 is equal to 8, which is a false statement. This is called a contradiction. It's a statement that could never possibly be true, no matter what x and y might be. So all of the algebra, which was completely legal algebra, led us down to something that is just categorically false. Anytime we lead down to something like this via all of our algebra, we end up with something that's false. We end up with what we call, again, a contradiction. That is our indication that there's no solution. There's nothing left to solve for, but we also have something that just can't be true, period. There's no way this can ever be true. So that is our indication that there's going to be no solution to this particular problem. Well, if that's what no solution looks like, what about infinitely many? What's that going to look like? It's going to be similar. So again, same idea, label your equations, pick a variable to isolate. In this case, the second equation and the x, that's going to be the easiest one to isolate because that x is the only variable that has a coefficient of 1. Now you'll notice in all three of these we isolated an x. That was just because of these specific problems. Here with the first one, we could have isolated a y just as easily, which means we just would have substituted for y. We would have solved for x first and then solved for y second. You'll get the same answer. It's not going to matter. It's ultimately just your choice which variable you pick, which equation you pick. So equation 2, we're going to isolate the x. So we have a plus 2y. I'm going to subtract it and move it over to the other side. So we now have an expression of x in terms of y. So wherever we see an x, we can put a 4 minus 2y instead because they are the same thing. Now here I used equation 2 first, which means I now have to use equation 1. I have my expression for x, so I'm going to substitute this in place of x. Again, make sure you put parentheses around that because now the 2 has to distribute to both of the things we substituted. So 2 times 4 is going to give us 8. And then 2 times negative 2 is going to give us negative 4, so negative 4y. Now again, notice we had the plus 4y that was already in the equation. So our like terms reduced down to 0. So almost the same thing here happened in this system. The one difference though is what results after those like terms reduce. What are we left with on the left and what are we left with on the right? Well, on the left we have a positive 8. And on the right, notice that we also have a positive 8. So the resulting equation after those variable terms reduce is going to be 8 is equal to 8. In this case, it's actually a true statement. It's true by default. There's no need to have a value of x and y in order to say that 8 is equal to 8. 8 is equal to 8 is just a true statement. But it's a true statement that still leaves us unable to solve for our variables. When we substituted, the variables ended up being eliminated. So there's no way to uniquely solve for x, uniquely solve for y, because they just disappeared. You might think, okay, well, it happened when I substituted for x. Why don't I just go back and try to solve for y? Which you certainly could do. You will find the same thing. You may not get down to 8 equals 8. But you will get down to another true statement that still leaves you without a variable to solve for. So because we can't solve for a variable, but we did end up with a true statement, that is our indication that there are infinitely many solutions. Now again, do not write all real numbers because that's not the solution. Our solutions represent ordered pairs. So any ordered pair that works for one equation also works for the other. Well, there are infinitely many ordered pairs that work for any individual equation because if we were to graph them, we have a line that's got infinitely many ordered pairs on it. So the infinitely many just means any ordered pair that works for one equation works for the other. So that whole set of ordered pairs represents all the possible solutions to our system. Now we have one additional algebraic technique that we can use to solve these kinds of systems. Specifically, what happens when it's difficult to isolate a variable? So you'll notice in all 3 of these systems that we looked at, there was at least one variable that could easily be isolated because there was at least one variable that had a coefficient of 1. What if you have a system where none of the variables have a coefficient of 1, which means ultimately isolating a variable would require you to divide? Again, dividing, the issue with that is we may create fractions, whereas we didn't originally have any fractions in the problem. Fractions are okay, but most people probably want to avoid fractions if they can, myself included. So when substitution is not a good option, when it's not easy to isolate a variable, we have another technique that we can use. This is going to be the most general algebraic technique, and we're actually going to build on this technique a little bit later when we talk about more complicated systems. So we call this the addition method. Sometimes you'll see it called the elimination method. So substitution is so named because the special technique we're using involves substituting for a variable. Well, here we're adding and we're eliminating via our addition. So this particular method, again, sometimes you see it called addition. Your textbook, I believe, calls it addition. Sometimes you'll see it called elimination. Same concept. Essentially, it relies on this algebraic principle that doing the same thing to both sides of an equation generates an equivalent equation. In other words, you do something on one side, as long as you do the same thing on the other side, then everything remains in balance and you still have something equivalent to what you started with. Now, from a practical standpoint, what does this mean in terms of how we're going to use this idea of keeping this equation in balance? It's going to mean 2 things for us in terms of how we're going to use this idea. So number one, based on this idea, we can multiply each side of the equation by the same constant and still keep things in balance. So say we multiply both sides of the equation by a 2. Well, as long as we do it to both sides, everything is still in balance. Say we multiply both sides of the equation by a -1. Well, again, as long as we do it to both sides, everything is still in balance. So doing the same thing to both sides of the equation gives us something that's equivalent to what we started with. Now the next version, the next thing we can do based on this idea is ultimately what's going to cause the elimination, what's going to sort of solve the system for us. So in addition to multiplying each side of the equation by the same constant, we can also add a constant multiple of one equation to another. Now, what we're really doing here, that seems a little bit vague. It's going to make more sense when we actually put some numbers in there, and I'll explain to you how this relies on this idea of balancing the equation when we actually have some numbers. Now, the goal here is to eliminate one variable but leave the other variable in the problem. And this is going to result just by default from doing what we're going to do. Rather than substituting to get rid of a variable, we're going to combine equations together, which will also get rid of a variable, leave us with one. As long as we can find an equation, some version of the originals that only has one variable, then we can uniquely solve for that variable, and then we can replace it in another equation and solve for whatever additional variable we want. Now let's look at some new ones. Here, for this particular first system, technically we could do substitution if we wanted. This x in the second equation, that could be isolated pretty easily. We could substitute it into the first equation. Substitution would be an option here. What I want to show you though is how we would use a different technique. So what we're going to have to do is we're going to pick a variable, either variable in either equation, and we're going to eliminate it. Now specifically, I'm choosing to eliminate x. So we want to eliminate the x variable entirely. So notice in the first equation, we have a 2x. I want you to think of what you would have to add to a 2x to get rid of it. Or more specifically, just focused on the 2. Forget about the x for a minute, just think about the 2. What would you have to add to a 2 to get rid of it? Well, you'd have to add a -2 to it. We call that the additive inverse of 2. Additive inverses combine together with addition to cancel one another out. In other words, to leave a 0. Well, the same thing applies here. If we have a 2x and we want to eliminate it, we want to get rid of it, then we'd have to combine it with a -2x. So what we want to do is we want to take this second equation and we want to sort of manipulate this equation so that instead of having an x here, we actually have a -2x here. The -2x can then be combined with the 2x above it, and that will eliminate the x terms entirely. So ultimately what we're doing is we're using this particular idea, the idea that we can multiply, take an equation, multiply each side by the same constant, and it keeps everything in balance. We're multiplying by a strategic constant with a particular goal in mind. So for our second equation, we want to multiply that equation by a -2, the whole thing by a -2, in order to be able to cancel with what we have in the first equation. So by means of notation, we're taking equation 2 and we're multiplying the whole thing by a -2. So I'm taking -2, I'm taking that whole equation, and I have to multiply the whole equation by a -2. Now technically this is not exactly proper notation. Technically you would write parentheses around one side and then parentheses around the other side, also multiplied by -2. But the general idea here is that we want to distribute a -2 to every single term in the equation. Easiest mistake here is you do it to one side and you forget to do it to the other side. You have to apply this particular operation to both sides in order to keep the equation in balance. So when I distribute that -2, that's going to be -2x. -2 times 3y is going to be -6y. And then -2 times 36 is going to be -72. Be very careful with your signs here. Flipping a sign, again, makes a big difference. Now what we're then going to do is we're going to take the resulting equation, which is equivalent to the original equation 2. It just differs by a constant, but otherwise it's an equivalent equation. And we're going to combine it with the other equation, the one we didn't use, equation 1. Why can we do this? Well, as long as we're doing the same thing to one side that we're doing to the other, we still keep things in balance. Now here, we're taking one side of the equation, we're adding those two sides of the equation, and then we're adding the other two sides of the other equations, okay? Why is this legal to do? Why can we do this? Well, if we're saying 2x plus y is equal to 32, which is based on the equation we had in the actual given problem, adding a 2x plus y, adding that to something is the same thing as adding 32 to something. So adding 2x plus y to one side of the equation is the same thing as adding a 32. So 2x plus y, we could add it to the left, we could add it to the right, but rather than adding 2x plus y on the right, we're going to add what it's equal to, which is actually 32 in this case. So it's just the fact that we're adding the same thing to both sides, but we're adding different forms of it to both sides. So we're adding the 2x plus y on the left with this goal of matching up those x terms and eliminating them. We would normally take 2x plus y, add it on one side, and then add the exact same thing on the other side to keep things in balance. But because 2x plus y is the same thing as 32, then rather than adding this specifically on both sides, we can just add a 32 on the other side instead, knowing that these are ultimately the same thing, and we really are adding the same thing on both sides. We're just adding different forms of the same thing on both sides. But again, we're doing it with this goal of being able to eliminate one of our variables. So in this case, the goal was to eliminate x. We had a 2x from the first equation. So we multiplied the second equation by a negative 2, which then gives us equal and opposite terms that will cancel when we combine things together. Now ultimately everything else, we just have to combine what we actually have left over. So negative 6y plus y is going to give us negative 5y, and then negative 72 plus 32, be very careful with your signs, that's going to give us negative 40. So notice what results after the elimination is an equation where the x is eliminated, hence the term elimination. So we call it addition because we're adding two equations together, but we call it elimination because the result is that one of the variables is eliminated. So what we now have is one equation with one variable. We can divide that negative 5. Keep in mind you're not adding it here, you're multiplying by a negative 5, so you're going to divide it from both sides. And that's going to give you y is equal to 8. Now once you have one of the variables solved for, now you're essentially going to do the same thing that you did with substitution. So you're going to go back to your original equations, plug in that value you just found, and then solve for whatever value is left. You can plug into either equation, doesn't matter. Here I picked the second one, just because once I plug in the y, the x is going to be easy to solve for. So x plus 3y is equal to 36. So x plus 3 times our y value, which is 8. 3 times 8 simplifies to 24. So in order to isolate our x, solve for it, we want to subtract a 24 and move it over, which is going to give us x is equal to 12. So the unique solution to this system is going to be the ordered pair 12, 8. So you might recognize this system. This was the first one we looked at. This was the ticket problem system. We got that x was $12 and then y was $8. Well, here we go. This confirms it. So this is, again, another technique you can use as a substitute to graphing. Sometimes graphing is a good option, sometimes it's not. This at least confirms algebraically that 12, 8 was, in fact, the solution to this system. Now let's look at the next one. This one's a little bit more challenging in the sense of how do we actually determine what we need to do to get rid of a variable. So in this case, because one of the variables had a coefficient of 1, it was pretty easy to determine what we would need in order to get matching variables to cancel. So if we have a 2x, well, we need a negative 2x. So just take that second equation, multiply it by negative 2, and then you have things that match up and cancel. Now this is a little bit different in the sense that there's not an equation that has a variable with a coefficient of 1. And also, there's not going to be anything that it's going to be easy to multiply just one equation by in order to get what we want. So we need to pick a variable to eliminate. Now, how do you strategically pick a variable to eliminate? Well, again, ultimately it's not going to matter, but in this case, I'm going to pick the y to eliminate. And my logic here for picking y is the fact that the terms already have opposite signs. Think about what we had to have right here. We had a positive 2 and we needed a negative 2. They needed to be the same, but they needed to also have opposite signs so that when we combine them together, they actually do cancel out and give you a 0. So positive 2 and then the negative 2 that we got from multiplication, that was what reduced to 0. The fact that they were equal, but they were also opposite. Okay. Now here with the y's, notice we already have a term that's negative and a term that's positive. So the opposite sign component, that's already taken care of for us. We could eliminate the x's, but we would have to keep in mind that we're starting with two things that are positive. So ultimately, when we choose what to multiply our equations by in order to get those equal and opposite coefficients, one of the equations would have to be multiplied by something negative in order to take those two positives and get the opposite sign that we need in order to combine and eliminate. So I'm going to pick the y's because that part is already done for me. Now I have a 2 and I have a 5 and I want to eliminate. Normally I would take the smaller number and multiply it by something to match it to the bigger number. But it's not all that simple to take a 2 and multiply it by something and turn it into a 5. If we were to take a 2 and multiply it by a 2, well then we'd get to a 4. If we multiplied it by a 3, then we'd get to a 6. So 5 is right there in the middle. What that ultimately means is that if I wanted to multiply equation 1 by something to turn that 2 into a 5, I would actually have to multiply by something fractional, which I'd like to avoid. So another option, rather than picking one equation and multiplying, is you can pick both equations. You can multiply each of them by something strategic, and that is also going to give you something you can use to eliminate. So you don't have to just multiply one. You can multiply both equations by something and then use the two resulting equations and eliminate with both of those. So what we're looking for is a multiple that's common to 2 and 5. The easiest way to get these to match up so that they're equal and opposite is just to multiply by the other number. So if I were to take my first equation and multiply by a 5, and then take my second equation and multiply by a 2, then automatically I'm going to end up with the same number, with the first one being negative and the second one, I was about to sneeze, excuse me. Okay, there we go. Okay, so first one is negative, second one is positive, but then we would have the same value. They would be equal and opposite. So multiplying by the other value, as long as we have those two different signs, will also give us something that's able to eliminate. So I'm going to take that first equation. I need to have something that cancels with the number below. So I'm going to multiply that equation by a 5. And then I'm going to take the second equation and I'm going to multiply it by a 2. So what's going to result for our y terms? Well, if I multiply this first equation by a 5, that's going to give me a negative 10y. And then if I multiply my second equation by a 2, that's going to give me a positive 10y. So it will give me those two equal and opposite coefficients that I need in order to be able to cancel this particular variable. So first equation multiplied by a 5. So distribute your 5, make sure it distributes to all three terms. So 15x minus 10y, and then 5 times 8 is going to be 40. Make sure you do it on the right-hand side as well. And then the second equation multiplied by a 2. So 2 times 2x times 5y and times negative 1 is going to give us 4x, and then positive 10y, and then 2 times negative 1 is going to be negative 2. So again, we did this with the goal of being able to eliminate a variable. In this case, we now have y terms that have equal but opposite coefficients. So that negative 10, that positive 10, that reduces and it eliminates the y, leaving us with an equation that only contains the variable x. So we just have to combine what's left at this point. So we have 15x, and we're adding another 4x, which leaves us with 19x in total. And then 40 combined with a negative 2 is going to give us 38. So 19x is equal to 38. Divide the 19 to both sides, and that's going to give you x is equal to 2. So that's half of our solution. Now we need the y. So take that 2, pick one of the original equations, and substitute. Again, it doesn't matter which one you choose. I picked the first one here, probably just because the second one had a negative as part of it. Ultimately, it doesn't matter though, your choice. So I'm going to plug in x equals 2 to that first equation. So we have 3 times 2, which is a 6. And now we want to isolate the variable that's left, in this case a y. Now be very careful here with your signs. You have to think about what's actually happening on the left hand side and what it would take to eliminate each of those components. So the 6 is not actually subtracted, it's actually added. It's a positive number that's being combined via addition to a negative y term. But because the 6 itself is positive, we have to subtract it in order to move it over. So subtract it on both sides, and then 8 minus 6 gives you 2. And then negative 2y is what's left on the left-hand side. So we have negative 2y is equal to 2. Divide the negative 2. Be careful, don't add it. It's multiplied and it's a negative 2, so we want to get rid of it. We have to divide it, and that's going to give us y is equal to negative 1. So x is 2, and then y is equal to negative 1. That's going to be the unique solution to this system. Now we're going to look at some applications next, but before we do, how do you identify no solution? How do you identify infinitely many solutions when you're looking at elimination? Well, it's ultimately going to look the same as it did with substitution. So let's revisit that real quickly. So with our no solution situation, remember we substituted, and then the result of substitution was an equation that was just categorically false. We don't have any variables left to solve for, but what results once the variables eliminate is something that is just blatantly false. The same thing will happen with elimination. So if once we eliminated, somehow we ended up eliminating both variables, but we were left with an equation that was false, then the same thing, it would look essentially the same as it looks right here. We would have an equation that's false, and that's our indication that there would be no solution. Same thing for the infinitely many case. We did our substitution, the result was elimination of both variables, but we had an equation that was just true. So once we have an equation that's true, but we still can't solve for any variables because they've both been eliminated, that's our indication that there's infinitely many. Same thing here with the addition technique. Once we went through, if both variables had been eliminated via our multiplication and then our combination, but we ended up with something that's true, then again, that's our indication that we have infinitely many solutions. So you'll look for the same thing in either of those cases. Just using substitution versus using addition, you'll be able to identify those special cases in the same way. So let's talk about a couple more situations where we would actually use a system of equations. So we looked at that ticket problem to start with. That's kind of a contrived situation though. How would you actually use a system of equations in an actual context, in a real applied context? How could it actually be used in real life? Well, we can do what we call break-even analysis. And I want to say we've looked at this before, talking about cost, revenue, and then profit. I think we looked at that in terms of functions. Let's revisit this, but let's think of it more as a system of equations. So if a company knows fixed and variable costs per unit, it can use break-even analysis to compare costs and revenue. So the term breaking even means that cost and revenue are the same. Another way of saying that is profit is 0. So there's all different ways to communicate this same idea. But if we're just talking about comparing cost and revenue, then the term breaking even means that our costs and our revenues are exactly the same. So in other words, revenue, think of that as what comes into our cash register. Cost is all the bills we have to pay at the end of the day. So if you have to take all the money from the register to pay your bills and you don't have any left over, but you did pay all your bills, then you're in the situation where cost and revenue are the same and you're breaking even. So in this case, you're neither losing money nor are you making money. So what we know is at that point, if we make any more than that particular value at the break-even point, then we end up having a profit. If we make any less than that particular value at the break-even point, then we know we are posting a loss. We know we're losing money. Now, how does this fit in the context of this section? Well, the cost and the revenue equations create a system of equations. So not only can we look at them from the standpoint of functions and thinking of functions and how they relate to one another, we can also think of it in terms of a system of equations, and that's what we're going to do here. So we talked about how you would generate those functions. All of that is still the same. So for example, a manufacturing company produces a single product. Its plant has fixed costs of $65,000 per day. So overhead, think of keeping the lights running, making sure your taxes are paid, all that stuff. And then also variable costs of $1,100 per unit produced. So you produce 1 unit, this is how much it costs. You produce 2 units, double that, that's how much it costs, and then so on and so forth. So remember the $65,000, because that's fixed, you have to pay that no matter what. Whether you make anything or not, you have to pay this amount. This amount is then multiplied by how many items you produce, and that's going to give you the variable component of your cost. And then each product is sold for $1,600 at retail. Now that does not immediately mean that you make a profit of $500 per unit, because you still have to have enough revenue to cover those fixed costs. So the difference between your variable cost and the price you sell it for is $500, but that additional $500 still has to be enough to take care of the $65,000 that you have to cover no matter what. So first thing we want to do, let's write the cost and revenue equations, and we're going to let our variable X be the total number of units produced and sold per day. Now we have to again assume that every item produced is immediately sold. We can't have a surplus. So cost, we produce something and we have a cost for production. Every time we produce something, we immediately sell it. So nothing's left on the shelf at the end of the day. That's kind of how we can think of it. So our cost is going to be our variable cost per unit times the number of units we produce. That's our variable X, plus the $65,000 worth of fixed costs that we have to pay no matter what. And then our revenue is going to be the price we charge per unit, which was $1,600, multiplied by how many units we produce and sell, which again is also X. So we have to assume X has the same value in both of these situations. So these are going to be our two functions. Say we wanted to have the profit function, the profit equation. Well, remember revenue minus cost, that's our definition for profit. So if we wanted to generate an equation for profit, take your revenue expression, take your cost expression, subtract them, and then the resulting expression represents your profit. So then our next question is how many units must be produced and sold each day for the company to break even? Well, what do we know about breaking even? Again, we know that that means that cost and revenue are the same. So if you were to take your expression for cost and set it equal to your expression for revenue, that represents the situation where we are breaking even. So cost is equal to revenue represents the situation where you're breaking even. So set your cost and revenue equal, and then the goal is to solve for X. Now you have one equation that has exactly one variable. So this is kind of like a substitution situation. We're substituting in an expression for C, we're substituting in an expression for R, and the resulting equation contains only one variable, in this case the variable X. And remember, X represents the total number of units produced and sold, so whatever X value we get here, our question was how many units must we produce and sell to break even? That X value is going to be the X value we want. So notice we have matching X values on each side. We need to get all of our X terms on one side. Normally we move things to the left just for whatever reason, but you can move them left, right, it does not matter. Because the X term over here is already isolated, I would suggest moving from the left to the right instead of moving right to left. It's going to be a little bit faster. So we want to subtract 1100. It's a positive term. So 1100x, subtract it, move it over. Subtract it on the right hand side, and that's going to give you 500x. And so that leaves us with $65,000 on the other side. So divide by the 500, which is multiplied by x. Notice this 500 here. What does that represent? Well, that's the difference between your price and your variable cost per unit. So if you take that amount of profit, what we can think of kind of like the profit per item produced, we also have to divide that into our fixed cost. And that's going to tell us how many units we need to produce in order for that difference of $500 to cover the full $65,000. So divide the 500 into 65,000, and we're going to get 130. X is 130. In this case, 130 units. So if we produce 130 units exactly, we won't be making money, but we won't be losing money. Obviously, we can cover our variable cost just by charging more, but we need to produce 130 units in order to be able to cover that $65,000 worth of fixed costs. So anything less than 130, we don't actually cover all our costs, and anything more than 130 units, we know we're making a profit. So this is another perspective for the break-even analysis. You can think of this as your system of equations. Think of the cost and revenue kind of like Y. They're essentially Y values, they're outputs. In this case, they represent dollar amounts. And then they're each equal to an expression. Well, if we want cost and revenue to be equal, we can also substitute in those equivalent expressions. And that gives us that one equation that has that matching variable. We can then solve for that matching variable. Now let's look at a new situation. This is an economics-based situation. So one of the fundamental concepts in economics is this idea of supply and demand. Supplying a particular product based on a certain pricing model, and then what's the resulting demand? In other words, how much consumers want in terms of that product, again, based on how the product is pricing. So in a free market economy, pricing is determined by this relationship. How much suppliers are willing to put onto the market based on how they can price, and then how much consumers are willing to buy based on, again, how items are priced. So in general, suppliers, the people making the product, will supply more when prices are high. Why is that? Well, that's because they're planning on making more money. The higher they can charge, the more money they expect to make off of their items that they're selling. And when the price-supply relationship, think of that as an equation. Price is one of the variables. Supply, or the amount supplied, is another variable. In this case, the slope of that line will be positive. So we can think of that as a line that's oriented like this. So going from left to right, it's oriented upwards. So as the price increases, the quantity supplied also increases. It goes up. Now, consumers will demand more. They're willing and able to buy more when prices are low. It costs less, they're more likely to buy it, and they have more money, they have more funds in order to be able to buy it. So when prices are low, the amount demanded tends to be higher. So when the price-demand relationship, again, is linear, the slope will be negative, which means sloped downward, something like that. Or I guess, there we go, that's better. So as the price increases for consumers, the amount demanded decreases. So suppliers want prices to be high, consumers want prices to be low. How do you balance this out? How do you actually find the right price so that you're maximizing how much will go on to the market, but you don't end up with so much on the market that people aren't willing to buy it and you have what we call a surplus? So in a free competitive market where we're actually using these forces of supply and demand in order to determine appropriate pricing, the price tends to move to what we call an equilibrium price, sort of the balancing point, and then the matching quantity. So at a particular price, suppliers will apply a certain amount, consumers will buy a certain amount. We're looking for the price where the amount supplied and then the amount demanded are going to be balanced. That's what we mean by equilibrium. How much is on the market and how much people are willing to buy, those particular values are balanced. That quantity is balanced. And that's always going to be where supply and demand are equal. So supply, again, think of that as the relationship between how things are priced and how much suppliers are willing to put onto the market. And demand is how things are priced and how much consumers are willing to purchase off of the market, purchase from their actual suppliers. When those two particular relationships are equal, kind of like the cost and the revenue situation, then we're at a particular point that we call equilibrium, where everything is imbalanced. We can think of that as the ideal situation. So this again is going to generate a system of equations. We can think of supply as an equation, and then demand is also an equation. Now, generating these equations is going to be a little bit more complicated than generating the cost and revenue equations. So I want to talk about a general linear model for how we would generate these types of things. So that's going to be our basic linear model. This is a form of a linear equation that we call the point slope form. We call it point slope form because in order to write the linear equation, we need to know a point on the line, and we also need to know the slope of the line that we're modeling. So the variable m represents slope. Slope is defined as change in y over change in x. So if we take two y values and subtract them, and then take the associated x values, subtract them, take the ratio of those two values, that's defined as the slope of our line. If it's a positive slope, that means our line is oriented upward. If it's a negative slope, that means our line is oriented downward as we go from left to right. Now, this x and y, notice these don't have subscript, whereas these two do. The ones that don't have subscripts, those are the actual variables modeling the relationship between x and y in our equation. y1 and x1, in general, whenever you see variables that have subscripts, those mean we're going to substitute fixed values in general. So x1, y1 is any point on the line. All you have to have is one ordered pair that represents the relationship between x and y. You substitute those values in here, along with the slope that we find related between two ordered pairs. And then what results is a linear equation representing this relationship based on these particular values. So we're going to use this modeling technique, finding the slope, finding a point on the line. We're going to use it both for supply and for demand in order to generate the two equations in our systems. So let's look at this particular problem. At a price of $1.88 per pound of cherries, the quantity of cherries supplied is 16,000 and the quantity demanded is 10,600. So at $1.88, producers will put 16,000 pounds into the market, but consumers only want or are willing to purchase 10,600 pounds. So in that case, we have a surplus in terms of supply. There's more on the market than consumers are willing to buy. So what that ultimately means is $1.88 is too high of a price. Suppliers like it, but consumers don't because they're not willing to buy everything on the market. Okay. When the price drops to $1.46 per pound, the quantity supplied decreases to 10,000 pounds, and the quantity demanded increases to 12,700 pounds. So at $1.46, suppliers are only willing to provide 10,000 pounds, but consumers are willing to buy up to 12,700. So they want to buy more than is actually on the market. So that means that the price is too low. So the ideal price, the equilibrium price, is going to be somewhere between these two values. $1.88 is too high because there's more on the market than consumers are willing to buy. And then $1.46 is too low because there's less on the market than consumers are willing to buy. So what we're looking for is the sweet spot in the middle. Where do we have that sense of balance where the pricing is just right so that the amount supplied and the amount demanded, how much people are willing to buy, is actually balanced out? So first thing we want to find is the equation representing supply. Based on the fact that at $1.88, 16,000 pounds are supplied. And then at $1.46, 10,000 pounds are supplied. So we're going to think of X, our input, as being quantity. Now notice all these quantities are in thousands. So rather than writing 16,000 as our X value, we could just write 16 and think of our quantity being in terms of thousands. So our input is going to be quantity, and then our output is going to be price in this case. So 16,000 pounds at a price of $1.88. So as an ordered pair, that would be 16 for our X value. That's our quantity. Again, remember that's in terms of thousands. And then our output is going to be $1.88. And then the other value we have at $1.46, it's going to be 10,000 pounds. So 10 is our X value, and then our output is going to be $1.46. So these two ordered pairs represent supply and how it's related to particular pricing amounts. So think of this as XY and then XY. From these two ordered pairs, we can now find the slope that models the relationship between these particular amounts, these particular pairs of values. And this is based on the assumption that our equations are linear. There are situations where supply and demand are not actually linear, in which case this kind of model doesn't work. But because we're told that everything is linear in this case, we can use our formula for slope, and then we can use this particular model based on just either of these ordered pairs in our problem. So our slope is going to be the change in Y divided by the change in X. Now, which one you use first versus second in the formula ultimately doesn't matter, but once you pick a 0.1 and a 0.2, either way, you have to stick to it. So I'm going to do $1.88 minus $1.46. So we'll say this is Y2 and this is Y1, higher minus lower, okay? Once I pick this to be the first one and this to be the second, I have to subtract the X values in the same order. That's ultimately what you have to commit to once you pick your different values. So $1.88 minus $1.46, and then our denominator is going to be 16 minus 10. So now I just want to reduce all of that, and that's going to give me my slope. So let's go through that. So our numerator is $1.88 minus $1.46, which is going to give us 0.42. And then our denominator is going to be 16 minus 10, which is going to be 6. So we're taking 0.42 and we're dividing it by 6, which is going to give us a slope of 0.07. Now that's a positive number. That means our line is sloped upward. So because this number is small, it means it's sloped upward and it's not very steep. The higher the value, the more steep the line is. The closer the value is to 0, the closer it is to a horizontal line. But it is sloped upward going left to right. Now once we have the slope, all we need to do is substitute that into our model. So using that in place of m, and then x1 and y1, those can be either values from either ordered pair. So we can pick which ordered pair we want. We use this as 0.2, we use this as 0.1. We can use the other values if we want. Ultimately, we're just looking for some ordered pair that fits this relationship, and we're going to use that particular ordered pair to substitute into the model. So I ended up choosing the first one here. You'll get the same values if you choose the second one. So in this case, we're thinking of our input as x and our output as p. So rather than using x and y, here we're going to use x and p, just based on what our different values represent. So we have p minus our value for p, which is $1.88. We have our slope, and then x is our input minus the associated x value, which is 16. Now typically when we're representing something that's linear, we want to isolate the dependent variable, what we think of as the y value. So in this case, we don't have a y value, but we have p representing the relationship that we usually have between x and y. So we want to isolate p, clean all of this up, get p by itself. So if I want to isolate p and want to simplify all of this, first thing I need to do is distribute the slope on the right-hand side. So I'm going to multiply 0.07 by both terms in parentheses. So 0.07 times x. And then we also need to multiply it by the 16. So 0.07 times 16 is going to give me 1.12, and it was subtracted, so that's going to be negative. Now in order to isolate P, we want to take this dollar amount, it's negative, and we want to add it, move it over. Notice that it'll combine with the 1.12 because those are going to be the two like terms there. So we have negative 1.12 because it's negative term, and we're adding 1.88. And so that's going to give us 0.76. So this is going to be our price supply equation. X represents the quantity supplied, and then P represents the price that needs to result based on that quantity being supplied. Now we need to do the same thing for demand. So for each of these dollar amounts, remember we were given an amount supplied, and then we were given the associated amount that consumers were willing to purchase. We call that the quantity demanded. So at $1.88, consumers demand 10,600 pounds. So at $1.88, the input is 10.6. Remember, we're writing it in terms of thousands. So rather than 10,600, we're going to write 10.6. And then at $1.46 per pound, consumers wanted more than was actually on the market. They wanted 12,700 pounds. So 12.7 and then $1.46. Now after that, the process is essentially the same. We're finding the slope, so y2 minus y1 over x2 minus x1. Notice what happens when we simplify here though. So our numerator is still a positive number. But when we take the values in the denominator, so 10.6 minus 12.7, notice that's going to give us a negative number. We have a negative denominator. So when we take our numerator, which notice it's still the same thing because we still have the same y values, the same outputs, we have 0.42, and now we're dividing it by negative 2.1, which gives us a negative slope, which means that this particular line, if we were to graph it, is going to be sloped downward, which is standard for demand. Okay, so once we have that slope, we'll pick an ordered pair. We're going to plug it into our model. Again, let me put that back up there. That's going to be our model. Instead of y, though, we're using P. So P minus a particular value for P, in this case $1.88. I'm using the same ordered pair. And then our slope, negative 0.2. And then x minus the associated value of x, which is 10.6. Same process to simplify it down. So we want to distribute on the right-hand side. So negative 0.2x and then negative 0.2 times negative 10.6. Careful with your signs. Two negatives make a positive, and that's going to be 2.12. And then we also, again, need to isolate P. So we want to move the $1.88 over, combine our like terms, and our resulting equation is going to be P is equal to negative 0.2x plus 4. That is our price demand equation. So based on a particular amount being demanded, this is the associated pricing that results in that particular amount being demanded. So these two equations form our system of equations. So let's use those now. What we want to do now is find the equilibrium price and the associated equilibrium quantity. Now, it'll turn out that we find the quantity first, and then we'll use the quantity to find the price. What do we know about equilibrium? Equilibrium is like breaking even. It means things are imbalanced. But in this case, we're talking about supply and demand being in balance. So when we're at equilibrium, the amount supplied and the amount demanded are going to be the same. In other words, we've hit the sweet spot. So we're going to set these two expressions equal. This is our expression for supply, and this is our expression for demand. So essentially, if you think of both of these as being equal to P, then they also can be equal to each other if we're talking about the situation where everything is in balance. So our supply, 0.07x plus 0.76, and then our demand, set it equal, negative 0.2x plus 4. And again, notice now we have an equation that only has one variable. It has this variable x, which represents the quantity demanded versus the quantity supplied. Okay, so I want to combine my like terms. Now again, it doesn't matter which order we do things in, where we move things. Here, I would argue that moving from right to left is maybe a better idea because it's going to require us to add this term, which will take that negative term, it'll make it positive. So add 0.2x, combine it with the other x term. Now, be careful with your decimal places here. If you want to do this in the calculator, that's fine. So we have 0.07x, and then we're adding on 0.2x, so plus 0.2. So that's going to give us 0.27, and that's our coefficient for x. Now, if we move our x terms to the left, we have to move our constant terms to the right. So this constant term is positive. I have to subtract it to move it over. So we have 4 minus 0.76, and that's going to give us 3.24. So now we have a coefficient for x, and then we have that all equal to a particular constant. This is multiplied, so we want to divide it in order to move it over and isolate x. So 3.24 divided by 0.27, that's right, okay? And there we go, that's going to be 12. Now be careful though, because we're in the context of a real problem. What did x represent? X represented the quantity, but it was in thousands. So we noticed that all the poundage was in thousands. So rather than writing 16,000, 10,600, we shortened the numbers and then just represented in terms of thousands for our units. So if x is equal to 12, that means 12,000 pounds. That is going to be the equilibrium quantity. So that will be the amount that goes onto the market where everything supplied is also demanded. So ideally that means everything put onto the market will also be purchased. There won't be any surplus in either direction. So that is going to be our equilibrium quantity. Now we also want the equilibrium price. In other words, what price do we have to set in order for this to be the amount put onto the market? Here, it's basically a substitution, just like with any of the system of equations problems we've looked at so far. You can pick either of the equations, either the supply equation or the demand equation, and you're going to substitute that x value into it. I think I picked the second one. Yep. So P is equal to negative 0.2x plus 4. That represents our demand. Remember, demand and supply are equal here though. So whatever x value works here also will work in the supply equation. So x is defined as being 12 based on our relationship that we determined where supply and demand are equal. So I'm going to substitute in 12. Negative 0.2 times 12 is going to be negative 2.4. That's not a 24, that's 2.4. Let's verify that. So negative 0.2 times 12, okay, negative 2.4, and then we're adding 4 to that. And that is going to be 1.6. Now again, we need to put it in context. We're talking about a price, so the units are dollars, and then 1.6 means $1.60. So that's going to be $1.60 charged per pound. So that is the equilibrium price. That's the ideal price to charge so that suppliers are supplying as much as they're willing, but everything supplied is also being purchased by consumers. And if we go back to the original problem statement, when we were looking through this, remember $1.88 was too high because there was more supplied than people were willing to buy, but $1.46 was too low because there's less supplied than people are willing to buy. So people want more than is on the market. So $1.60, that's going to be the sweet spot there in the middle between these two values. So this gives you a couple of situations where you can actually use a system of equations. Systems of equations are very, very versatile. We use them in a lot of different situations, especially in situations where we're talking about business, talking about something applied, because in most real-world situations, there's not just one variable. There are multiple variables involved when we're trying to make decisions. So the system of equations allows us to represent the relationship among all the variables. Now here we've just looked at two variables and then two equations. What happens if you have more variables? What happens if you have more equations? Well, all the strategies we've looked at so far still apply. They can still be used. But if you imagine a situation where you have a bunch of variables, using substitution, using elimination can become very cumbersome. So in the next couple of sections, we're going to talk about another way, an additional way to solve a system of equations that's going to allow you to clean things up, represent your system in a shorthand, and it's going to give you a technique that you can use where your graphing calculator can do some of the heavy lifting for you.